So I'll give you an overview of the project. Now I'm going to start talking about kind of the measurements we made and how they relate to the research questions, or some of the questions we want to answer. So again, here was the sound, what the sea ice looks like typically before the last 2 seasons when we were there. This is 2018, which is one of the years we were there making measurements, and here's 2019. So you can see the sound really opened up earlier than typical. And so there's much to begin with in the sound. So just a little initial information. So here's what the sea ice concentration in all of Alaska looks like. So that's the percentage coverage for late March. Here's March 29 here. So late March, early April. I keep looking at these dates because that's kind of the date right before, that's kind of the peak ice concentration, right before it starts to decrease, and then when we see the breakup in Kotzebue Sound here eventually. So this is the typical peak time. This is what it looked like in 2018 when we were there. And this is what it looked like in 2019. So significantly less sea ice through all of Alaska for both years we were there. And this is what it looks like as it's decreasing from that time. Something that didn't make sense. So now so this is March here, and this is kind of a little image or movie that shows, animation that shows how the sea ice decreases over time into after April.
I'm sorry, I have just a question. You mean concentration, the depth of the ice?
No, this is actually just ice coverage, just the coverage. Not the thickness, just the coverage of it. So where there is ice in the Arctic. So it's decreasing from that time. And you can see that for 2018, it was pretty much gone in the middle of May, whereas other years, at least in the sound, other years it lasted up till June.
Do the currents have an effect on the ice coverage?
Here you go. So the Alaska coastal current comes up the coast from Alaska. There's a Siberian coastal current that comes down on the west side of the Bering Strait. And here you can just see, here's the cold water in the Siberian going south. Here's the northward Alaska coastal current that's warmer. And you can see the difference in the water mass, just what it looks like too. One more. So here's what it looks like. This is what the typical surface temperature looks like. So it takes that warm water, comes up the coast, and warm water is brought into the Kotzebue Sound. And that's exactly what we're going to talk about right now is what's driving the sea ice change in the river, that channel that we were interested in, why it breaks up. So here is Kotzebue. And as I mentioned, showed you that satellite imagery. Here's kind of this cyan here, this region. That's the land fast ice. So that's ice that grows from the land. And you can see here's the front of that is typically out of the mouth of the Sound, as we showed in the satellite imagery. The darker blue areas here are what the sea ice coverage is. So ice that grows in the ocean itself. Historically. And I also mentioned, just to highlight, that we are looking at this time frame here. Here I showed June, July, because that's typically when the ice would break up. It would start to break up in early June. What we're noting, when we were there, we started in late April and would make measurements through May, because this is when we were noticing that the ice breakup was starting to occur earlier. And so we want to catch that melt season of when the ice breaks up. So again, here's what the sound looks like the year we were there. Here's the outer ice edge, landfast ice edge here. Here's the sea ice coming in and out. And you can see a little bit of the channel right there. So there's an interest in the marine mammal use of sea ice. That's why we're looking at this. Requires measurements of the sea ice mass and the momentum balance. And it requires local measurements of sea ice fracture and movement. So we went through all that before. So why was there so little sea ice in 2019 was one of our questions. What determined sea ice transport in the Kotzebue Sound? That was another question. And what environmental factors control marine mammal use of Kotzebue Sound? So these are all the questions we want to kind of address or start to address with the data that we have. So this is this April sea ice extent since 2000. So this is what I'm going to show here is the years that it was covered by ice. So the color that's white means it was always covered for the last 20, since 2000, it was always covered by sea ice. And that was 2019, as I mentioned earlier. If we zoom into Kotzebue and look at that same landfast ice extent. So in 2000, the landfast ice was all the way out to here at the edge of the sound. And it forms in February, March, a little earlier, maybe January. And it persists without moving until the main breakup event. And so the white area, it would be the percent of years that are always covered by ice. So you can see the mouth, this ice edge really is maybe vary a little bit, but it does kind of cover most of the sound, except for our, 2019 was an anomalous year where the red is where there was ice during that year. And one of the elders told us that they used to go out there this time of year, meaning April, because they knew the ice was going to be at least 5 foot thick. So they had no problem going out on the ice. It's frozen solid all the way out to the lead. So all the way, they typically said it's frozen solid. Whenever the lead was out here, it was always frozen solid. What's going on? Oh, right. So I mentioned the rivers. There's two rivers, the Noatak River that comes down from the north and the Kobuk River, which comes from the east. And both of those kind of merge in the river in this back sound here behind this peninsula, the Kotzebue Peninsula. And they form this channel, they merge and they have this channel that comes out here, right? And we also have the Alaska coastal current that comes up the coast and brings ocean water into the ocean, into the Kotzebue Sound. So there's the picture of the satellite over that same location. And you can see here's the Kobuk, the Noatak River, and here's where they kind of merge right in here, and there's the channel. But there's still ice there, but you can see it start to go away. So this is a really important slide, this movie. I'm going to show it a few times. So this is what typically the ice breakup looks like. So here's the beginning, it's frozen out to the sound out here. Right in the beginning, you'll start to see in the channel here, right here in the beginning, you see that it blew up and that actually starts to break up. Right when the channel starts to melt, it reaches the other part of the out in the sound, and that kind of initiates the breakup. You can start to see it crack and become destabilized as soon as it breaks up. So there's right there, that crack. So the idea is that the river is driving the initial breakup of the sea ice. So we put a little measurement system right where that red dot is in channel to see that the relative roles of the ocean, the river, and the atmosphere are in the freezing and melting of the ice. Here's a zoom in a little more. We put it right there. You can see from the satellite picture here that this is of the ice surface. You can see that it is starting to melt a little, or thin. The ice is a lot thinner here than it is to either side of it. We had two locations for ice measurements. So one was a little bit upstream in the river here, and one was in the same location as the red dot. Upstream here, you can see the sea ice thickness. In both years we were there is less than a meter, at most a meter, maybe even half a meter in 2019. So it's very thin compared to what the elders are used to. They were mentioning 5 foot thick ice. Likewise, actually in our location in the channel, it was even thinner. It was at most 2 feet, not even 2 feet in 2019 when we were there, maybe 3 feet. In the year before, it was 3 feet. So it's much less than it was than the elders are used to. So the measurements we made in not only the thickness of the ice, but we measured kind of a few things, the atmospheric measurements. So what's the forcing on the ice from the atmospheric side? And then we measured the heat fluxes into the ice and through the ice, and the heat fluxes from the water side into the ice. So we're doing basically how much heat is coming in from the top, how much heat is coming in from the bottom, and then how much is going through it, that supports ice growth or not. So we had a string of measurements of thermistors to measure temperature and salinity of the water, of the ocean, of the river and ocean water. And we also had measurements of the currents using acoustic measurements, acoustic Doppler current profiler. So it measures the currents in the ocean, in the water. And we use those currents to figure out how much mixing there is and how much this temperature is being basically pushed into the ice, how much heat is being transferred into the ice. That's what that is. So the other thing is that the ocean brings salty water, and the river brings fresh water, pushes fresh water out. So the salt water from the ocean is pushing in on the tides, and then the river outflow pushes out with fresh water. So we can use that idea. We can use that to our benefit. That's the same thing. So that we know whenever there's high salinity pulse, that means there's ocean water is coming in. So here's the ocean water coming in. Here it comes in again in blue. That's the ocean salinity increasing. And every time you see the salinity increase, you see this increase in temperature. So the increase in that delta T that I mentioned, that I talked about here. So how much heat there is, how much warmer it is above freezing. So you can see every time the ocean water comes in, there's warmer water. It brings warmer water with it. And that's really important to why the ice thickness is bound where it is. It's not as thick as it typically is, because there's warmer water being brought in that's basically capping how thick the ice can be. So the ocean is the primary source of heat to the ice in the wintertime. We also had a measurement out here in the ocean, or near the edge of the ocean, or the sound, to see what is the water that's coming out of the river when it makes its way up out of the sound. Do we see a similar signal? So in the fall, so we had that out there the whole year, as opposed to the red dot we only had there for when the ice was there. So in the fall, when the salinity goes down, the temperature goes down of the ice, of the water goes down. And in the spring, which is the same time we're there at the red, when the salinity goes down, the temperature goes up. So meaning the warm water. So it's let's go back to the little trace. Sorry, there's lots of little things. That trace. Oh, I got ahead of myself. Sorry. I'm going to catch up now. So we already said that the ocean is bringing warm water in to the channel. And then eventually the river is going to carry that, the circulation pattern brings the water out to the blue dot. So it comes in from the bottom here. The warm water comes into the channel, and that caps how thick the ice can get. And then the water goes out up the north side there. And in that location, we see that when that fresh water comes out, right, because it's right near the ocean, is the warmer water that we saw coming in from the south. So it's the ocean water is coming into the sound. It's capping how thick the ice can be, and then the river outflow mixes back up with that warmer water, and it goes out the north side of the sound. So the Kobuk and the Noatak rivers exert a primary control on the formation and breakup of the landfast ice. So the upstream river temperatures are likely to be a useful diagnostic tool for anticipating both the freeze up and the breakup. We mentioned upstream temperatures because those would be easy to measure, as opposed to measuring the water out by the river, by the sound. So the success of future bearded seal hunting seasons, because that's the bearded seals want the ice breakup, depend more on the conditions in the rivers than the oceans. Sorry. So this is just a schematic diagram of the fall and the winter, and I'll just take you through it. So in the fall, the ice extent here influences the extent of the river buffer. So the fresh water floats on top of the ocean water, buffering heat away from the ice. So the salty ocean water is coming in, but in the fall you have this strong river water coming out, which is colder than the ocean water. In the spring, eventually the river water becomes warmer and the ocean water is colder, and because it's fresher, it still rides on top, and because it's warmer, it's going to melt more quickly. So that's kind of a summary of why, or what the processes are for the ice freeze up and melting. But what other processes are important? The surface processes of the ice are important as well. But how do you measure these? How do you quantify these properties when the ice is unstable? So we were melting during the melt season, and you don't want to be on the ice really when it's melting. So as I mentioned, we're looking in this season of May, now early May through June. And we're using these high endurance drones. So they take off vertical, but they fly horizontal like a regular airplane. They can fly for 12 hours. So we would take off in the morning, fly all day, and come back in the evening with whatever payloads we were using. So we had a number of payloads. One were visible and infrared cameras. I'll show some examples of what we use those for. We used hemispheric radiometers, so they measure the solar radiation and the sky radiation, so that both heat and cool the ice. Hyperspectral imager tells us about what the surface properties of the ice are. And the meteorological flux package tells us about what the atmospheric properties are. So here's a picture of it in Kotzebue here. Here's the UAV team. Here we're prepping it before flight, and then here's a takeoff. I'm going to show a little takeoff here.
Looks good.
So this is all automated. It takes off,
Looks really good.
and then eventually it just switches. It starts flying like a regular airplane. And away it goes. And we can program it exactly where we want it to go.
Kotzebue radio unmanned 17 Charlie uniform at 500 feet above
We
the
actually
South
can
Lagoon. We're gonna slowly
transmit
start
all the
working our
data
way
back
south.
in real
Kotzebue.
time, so we can see what we're looking at in real time and remap where we want to go.
Touchdown mode.
And then it lands on it automatically. It's all, I make it sound very easy, but there's a lot of people to make it work, but it is very useful way to make measurements. And it's very efficient too, because you get the data back real time. You can say, you see something that you want to study and you say, oh, let's keep doing it. Let's stay right here and watch that evolve. There's another little picture from the chase plane. You can see this. There it is right there, flying out over the ice edge. Anyway, and there's Kotzebue. It's a beautiful, beautiful shot. So one thing, another useful thing about UAVs is that they're very steady, repeatable tracks. So here's 3 different flights, the same. We would just program it to go the same place, and it always went there within a meter. It was looking at the same spot on the ice. It also makes very low. There's no low vibration, so it's really good for making atmospheric measurements, turbulence measurements, and even imagery. So when things aren't vibrating, it's a nice stable platform. You get nice crisp images. So this is one of our indigenous council members, and he's talking about. I'm going to play this, and he's talking about the impact of the southwest wind on the sea ice and land fast ice, and just want you to listen to that, and then we'll.
On
What
the
is that?
horizon here, you can see some ice piles, what we call Ivanux. So I believe it was in February when we had a big storm that happened, and it was sometimes after February, after the ice formed over here. We had this west wind that this out here I would consider land fast ice. It's attached to the bottom. But beyond that, wherever on the open part, it's questionable whether it's stable or gonna remain there. But this side of the piled ice would be considered land fast ice, and it kind of happened late in the year, to where this ice that we're standing on is still developing.
So,
Excuse me for a moment. I just got another notice that I've got less than 10 minutes.
yeah, I know, I saw that. Thanks.
Okay.
I
I have a
will.
question for you.
Ed.
Is there any correlation with the North Pacific Oscillation?
Oh, we have not looked at that.
Okay.
So, as I mentioned, we have a number of measurement systems, and I'm going to show you just some example of the airflow, because Cyrus just mentioned that the west wind is really important to the ice breakup. So we would go up with our measurement system. When we're flying, we're measuring a velocity with our probe, but we also have to remember that the aircraft is moving. So we have to subtract off that motion to get what the real wind is. And from that, this is how we then take that measurement of the wind in red, and we get a co-spectrum, but that co-spectrum gives us the flux. But for this purposes, we want to make sure that we get a really good wind measurement to understand the timing of this strong southerly wind. As Cyrus pointed out, the strong reversal, the reversal is what in the wind leads to the breakup of the sea ice. So you typically get a west wind that's really driving hard, pushing the ice up against the coast. And then they see this reversal here. This is a reversal that we measured. So the direction changed very quickly. And right after that, you see this huge piece of ice break off. So the combination of this strong southerly west wind raises the local sea level and pushes the ice up against the coast. And then the east wind pushes that large fragment off and it breaks away. So there's a perfect example of the indigenous knowledge guiding our hypotheses. So we made measurements of the atmosphere, and I mentioned that not only is the ocean important, but the actual surface of the ice is as it changes is going to impact how much radiation is absorbed. So we can use the UAV to go fly around and map out what the properties of the ice are. So here's a picture of, if you were taking a satellite image, you can see it's pretty grainy. And this is how much resolution we get with that's over the same place with our UAV, looking at the hyperspectral imaging. And as we fly down the coast, this is just an example of us flying down the coast here of Kotzebue. And I just have the map out of what the hyperspectral imagery is going to show. And I just want to highlight these three different regions. So here in the beginning, you see that it's somewhat snow covered, but it's also pretty dirty. And then here it's kind of heavily starting to become ponded with some snow still. And here it's just heavily ponded, fully ponded ice. And there are those three locations really blown up. And each one of these will resemble different types of absorption of solar energy and also release of long wave energy. So specifically for this case, when we saw the ice break off, how does the surface ice change? How does the ice surface change during the melt and breakup? And how does this affect the exchange between the air and the ice? So we went out and we measured the long wave and the short wave, how much is being absorbed by the ice. There's the thermal one, it has the flat dome or the flat surface, and then the visible has the dome. And there's both upward and downward looking. So we measure the net flux. So again, here's the channel here. There's the instruments. So this is a transect. We flew right along the channel with the UAV. And here is what the albedo shows. So the albedo is the ratio of how much solar energy, how much sun is being reflected back by the ice. So here you see that it's more reflective closer to town here. And as you go out towards that place we see every time in the satellite image, right here is where it's starting to see more absorption. It's less reflective. So there's more solar energy being absorbed there. And this is where we see this breakup. So there's this combination of both the river and the ocean impacting how thick the ice is, but then it's impacted also by how much solar radiation is being absorbed at the surface. And this is what the surface looks like. So clearly there's much more ice cover in the beginning near the, and then at the end, there's significant ponding. So how does this ice connect to marine mammals? So hopefully we'll get cut off and I can just finish up with this. Again, ice breakup. So the first thing we want to do is map the marine mammal habitat. So now we're going to fly along with the visible and infrared cameras. And this is what, on the left is what the visible camera looks like, and on the left is the infrared. So the dark areas are cold ice, the warm areas are, or the bright areas are warm water. On the right is the visible. So the lighter areas are ice and the darker areas are the ocean. Similar here. This is another example of sea ice. On the right, sorry, on the right is the infrared. And that's, so it's, the ice is cold, the ocean is warmer. On the left are the visible images. So the white is the ice, the dark is the ocean. So are we coming up to close here? This would be a good place to stop and then hop back on.